to Chapter 5, Dynamic Routing. Yeah, routing protocols. You've already been working with them for a little bit, specifically OSPF, but now we're going to start talking about some of the different routing protocols and get a little bit more in depth into them. So, when we're looking at routing protocols, dynamic routing protocols are broken up into a series of categories. So we have interior gateway routing protocols or exterior gateway routing protocols. Interior gateway routing protocols are what we use for our internal or private network, and exterior is used for the internet. So how those work, for the primary focus of what we're looking at is interior gateway routing protocols. But in 229 we will get into exterior gateway routing protocols, looking at both the two forms of BGP known as eBGP and iBGP, which just stand for interior or exterior. So we can use BGP for our an internal network, but we can actually also use it for external, which is essentially the primary routing protocol for the internet. So all routes between your internet service providers, all the different internet service providers across the globe, all done through BGP. It's very cool. The only thing with it is that it is a little finicky, so not anyone can just go and say, hey, I'm going to plop a BGP router out on the internet. There are safeguards, because if you don't know what you're doing or you do it wrong, you can easily say goodbye to a good chunk of the internet. And what I mean by that is there are lots of different situations where this occurred. A couple of years ago, actually, a internet service provider in Africa advertised incorrect routes before checking them, and Australia disappeared from the world, at least from the internet, for a good couple of hours. So gotta be careful when you're actually setting up BGP. For the most part, you probably won't go ever set up BGP unless you go and work for an internet service provider or a very large company that needs to utilize it. So we'll talk more about BGP in later class, but just want to give you a little update on that. So our other routing protocols are interior gateway routing protocols. This should be a little bit of a review to a certain extent. We have two different types of routing protocols that we can utilize. There are distance vector routing protocols and link state routing protocols. So what we've been working with is link state routing protocols, specifically OSPF. So remember, our difference between distance vector and link state is that link state knows every single path and every single connection on all routes and the estimated cost to all routes. So when our routers establish convergence, where they know all routes and have talked to each other, that means they know every single potential path that they might need to take. It might not exist in their forwarding information base, their FIB table, which is also known as their routing table, but it does exist in the database itself. So an additional database. So in that database, it holds all routes and all potential information. So every router knows every single link and every single potential thing that could happen or potential path that they might need to take. Distance vector routing we haven't really worked with, but I have described, at least in prior classes. So if you've had me in a prior class, this shouldn't be too much new news for you. But remember, distance vector routing protocols are essentially like signposts. So it works very similar in essence to kind of like static routing. If I have three routers kind of lined up in a line, router 1, router 2, and router 3, if router 1 wants to send traffic over to the router 3 network, it still doesn't know how far away router 3 actually is. It just knows that if it needs to send traffic to router 3, it sends it to router 2, and it hopes that router 2 knows what to do with it. That's all distance vector it kind of works on. So distance vector focuses just very similar in essence to how static routing works, in the concept that if I don't know where something is, I just pass it to my next directly connected neighbor and wish it the best of luck. Link state, I know exactly how far away, in that same scenario, I know how far away router 3 is from me. So which one's better? Which one should we choose? Distance vector or link state? Grand scheme of things, they're pretty similar in terms of load and actual kind of how fast they are in routing traffic. EIGRP is a Cisco protocol. It was developed by Cisco, so it's kind of boiled down to if you're using all Cisco products, EIGRP is great. If you're using a mishmash or hodgepodge of different networks, probably OSPF is what you're going to be working with. But the other thing to kind of remember is that even for a good chunk of our kind of networks, unless you're working in a pretty big network, odds are you're likely just going to be running off of static routes for the most part. Static routes are technically are a lot less resource intensive on our actual devices, and if we have a stub network where we're essentially just pointing traffic one way, static routes are really the way to go. But if you have a larger network and multiple redundant connections, multiple different routers and stuff that you have to interconnect, say multiple different buildings together, routing protocols are a great option for kind of interconnection. So OSPF, EIGRP work great. So again, kind of already talked about IGP and or BGP and kind of getting into the different kind of setups. Again, with interior gateway routing protocols and exterior gateway routing protocols, interior is just that, it's for your own internal network. Exterior is just that, it's the internet routing protocols. So we talked about distance vector, we talked about link state. So remember also we have two different types of kind of forms of routing protocols. We have classful and we have classless. The important things to note is that if it is class full, it means that we are beholden to the routing, the typical network standards. So a class A, a class B, or a class C network. So, and all things fall into those categories. So a 172 network, 172.16 network will, by its definition, will be beholden to a class B, so it'll be a /16. If we see a 192.168, that by its general standard is going to fall into a class C network, so it will always default back to a /24. So class full routing protocols basically will only ever be one of those three things. Either a /8, a /16, or a /24, and they cannot be anything else. So we cannot use variable length subnet masks when we're working with that. So that can be a little bit of a problem. It can create what's known as a discontiguous network, where we are essentially over advertising between different areas. So if we look at, say, our issue right here, between these two sides, if router 1 from the 172.16.1.0/24 network is trying to send traffic over to the 2.0/24 network, well, what's going to happen if this device tries to ping across and goes, hey, I want to go over there, and we're using a classful routing protocol, well, that traffic is not going to know where to actually make it to it, because it's going to go, well, I know about that entire /16 network. And not only that, but the primary thing that they're looking at in this one is, if you look at router 2, in that same scenario, if we're using classful routing protocols, it's going to go, well, I know from, again, the 172.16 network, that's going to have to go back to being a /16. So it will auto summarize back down to 172.16 0.0/16, which means that if it tries to ping to that 1.1 network, it'll send traffic out both towards router 1 and towards router 3, and no traffic is going to make it to the two sides. So at best, we split our traffic. At worst, nothing works, and we don't see any traffic come back to us. So, classful routing, it has its place, but generally we don't, unless you're following those specific classful boundaries, you typically want to avoid it. So classless is the opposite. Classless is really what we want to utilize for the most part. So EIGRP and OSPF are two primary routing protocols that we utilize for interior gateway stuff, are classless protocols. Yay! So classless allows us to utilize variable length subnet masks. So we can use different whatever mask we want for our private networks. So going back to the exact same scenario, now if I advertise that I know about the 172.16.1.0/24 network on router 1, and I'm using a routing protocol such as EIGRP or OSPF, it will share that correct route to router 2 as opposed to over summarizing it to a /16. So that's the nice thing. Other things that are good to note too is IPv6 are classless as well. So all IPv6 routing protocols. Okay, so RIP v2, don't really worry about them. They're pretty old. You're not going to see them at all really in the real world. Maybe a little bit of RIP v2 if you're unlucky, but for the most part those routing protocols are all but phased out. So for the most part, the two primary routing protocols that you utilize are either EIGRP or OSPF. You will see CIS in certain places, but for the most part, again, that is for internet service providers, and that's again for their specific interior gateway routing protocols. So other times, for the most part, it's going to be like BGP for eBGP or iBGP for internet service provider. So again, it really boils down to, like I stated a few minutes ago, which one should you pick? Which one's better? Distance vector or link state, EIGRP or OSPF, Cisco or not Cisco? It doesn't matter, grand scheme of things. So the biggest trade-off between the two is that resource usage is a little bit higher on OSPF over EIGRP, and that's because of how link state works versus distance vector. So link state again has to create an entire database and every single link and understand every single link and every single path, and in order to do that, remember when we talked about OSPF in our last quarter, it takes a lot of additional traffic, so there's a lot of additional initial overhead. So those link state advertisement packets that get sent out, there's a vast majority of them that actually go through. So that's the general thing with that. With EIGRP, because it doesn't have to send out all those link state advertisements and constantly send out updates when something goes down, its resource usage is a little bit lower between the two. So overall, which one's better? It really doesn't matter too much. You will likely have to do a little bit more actual configuration or kind of fine-tuning on OSPF, especially if you're using a little bit faster network cables, such as like fiber or 1 gig or 10 gig lines. Because remember, OSPF was originally developed back in the late 80s, I believe, and back then 1 gigabit, 100 megabit, 10 gigs, that wasn't a thing. So you have to, so when it runs through its algorithm to determine how far away and what the specific cost is for everything, it is essentially just a short little division problem, but when it divides it so that the 100 megabit is equal, its cost is always going to be 1, a 1 gig is always going to be 1, a 10 gig is always going to be 1, so the cost is always going to be 1 between those three things. So that can be a little bad, because now if you want it to prioritize utilizing a, say, 1 gig line over 100 megabit line, by default OSPF might not know how to do that. So it's not too bad to fix it. You can just change up a small command on the relative bandwidth to basically tell it, hey, use this bandwidth instead. So not too bad, but good things to note. Again, if you have to choose between the two, EIGRP is for all Cisco all day, OSPF is if you're not a Cisco shop. And odds are you're probably not going to be a Cisco shop because Cisco is really stinking expensive. Okay, so I mentioned cost a minute ago, so we're going to go through this again, but it's good to kind of remember when we're talking about our different metrics. So a metric is basically what our different routing protocols utilize in order to calculate the best potential path to get to a following location. So RIP, our good friend that we talked about a little bit, and then I swore off of, that we'll never really use, but RIP utilizes hop count. So in this scenario where it's determining what its best potential path is, PC1, if it's sending traffic up to PC2 in this diagram, it'll send traffic to router 1. Router 1 will look at it, and it'll look and go, okay, well, what is my best path? RIP is only based off of hop count, so RIP doesn't factor in anything else besides how many routers do I have to go through in order to make it to my intended destination. And because it's only one hop away, so it only has to go from router 1 to router 2, it will factor in and go, right, R1 to R2 is the best path, even though that's a 56 kilobit per second line. Super slow. Now, if it was, say, OSPF is based off of bandwidth. And so it uses what's known as a cost method, where it does a short little bit of division in order to put together a relative cost number, as opposed to, say, you know, a T1 is 1.544 megabits per second. It doesn't calculate based off of that. It takes that number, divides it, and then comes up with a specific number that's going to be associated to kind of as a reference cost for that bandwidth. And what it does is it will add that up. So if we think about that, what does that actually mean when I say it's a reference cost number? Let's just say it's the number 100 for a T1 line. So if router 1 is trying to go across that line, it's 100. That might not be the exact number, but it does for our example. So if we look at this and it tries to go through this process and PC1 is trying to send traffic up to PC2 again, traffic goes over to router 1, and between the T1 lines, each cost is 100. On the 56 kilobit line, that's way slower than the T1 line, so its cost is going to be something like 1,000. So what it will do is it will add up the costs to determine what the best potential path. So from R1 to R3 is 100, from R3 to R2 is another 100, so it's a total cost of 200. And then if it adds in the additional cost right there, let's say it's a 1 gig line, so it has a cost of 1. So 201 from the perspective of router 1 to get all the way to PC2. But if it tries to go across the 56 kilobit per second line, that's 1,000, so it'll say 1,001 because that's still 1 gig line. So it just looks at it and goes, okay, well, what's the lower cost between, or relative cost between the two? And it goes, okay, well, 201 is a lot less than 1001, so I'm going to send traffic through there. So EIGRP does something very similar in essence to what OSPF does, but it also has additional variability or additional variables that it calculates based off of as well, besides just bandwidth. So it also factors in the following, which is delay, load, and reliability. For the most part, you don't need to worry about it. The primary thing to note is that EIGRP utilizes its most important variable for its route calculations is still bandwidth. But you should know that it does also need those other variables as well: delay, load, and reliability. We're going to talk a lot more about EIGRP in our following chapters, so don't worry too much about it right now, but you should know how